Hello, students. Today we're continuing with our study of energy. We're now in Chapter 8 of our textbook. Now, before I get into this, I want to say something about the topic of energy. You may have noticed that in the book, there doesn't seem to be an actual definition of what energy is. And it's kind of a slippery thing. I've seen books where energy was defined as the ability to do work, and then the same book would say, well, work is defined as what you do when you have energy available, and so it becomes a circular thing. So so basically, what I'm saying is, energy is not like a this, that, and the other thing kind of subject. It's like this kind of ball of ideas, this mix of ideas, and Newton. I think Isaac Newton was a very step by step focused person, and maybe that's why he didn't understand he never got to figuring out energy. It was too a complicated, fuzzy subject. There's another subject in physics that's kind of like that. It's quantum mechanics, where it's not just this idea, that idea, that idea. No, it's this mix of ideas, and then you have to kind of take a look at the whole thing, and then once you've sort of figured it out, then you sort of start over again. So with energy, once you feel like you've figured out what energy is, maybe take another look at chapters 7 and 8. Kind of work your way through it again. So anyhow, moving on. So let's talk about forces, and so we're going to divide them up into two categories here: conservative and non-conservative forces. And the word to conserve, it means to not lose. And in physics, what we mean is we don't lose some physical quantity, like we're not going to lose energy. Or maybe we're talking about not losing something called momentum, or not losing electric charge, and so on. So in this chapter, to conserve is going to mean to not lose mechanical energy. And so mechanical energy could be kinetic energy, that's motion energy. It could be gravitational potential energy, something we're about to study, and elastic or spring potential energy, something else we're about to study. Now, we say that friction is a non-conservative force because it causes us to lose mechanical energy. So in our diagram from before, I had potential energy, kinetic energy, thermal energy. And the combination of potential energy and kinetic energy, that's this combination, this is what we call mechanical energy. And if there is friction around our moving parts, well, that's going to take away mechanical energy, and it's going to cause heat, and it's going to move the mechanical energy into thermal energy. So what the point is, friction, it causes us to lose mechanical energy, and that's why we call it a non-conservative force. All right. Now, springs, the force of a spring, and the force of gravity, there's no, it's like sort of the opposite of friction. You're not losing, you're not converting energy to heat here. And so the mechanical energy is not lost with these. And so to understand that, let's look at some examples. All right, so the first example, it will involve friction. So you push a book across a desk, and it has friction. So you're going scooch, 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 and there's this rubbing going on between the book and the desk, and that causes heat to be formed. So, yeah, all right. So we've got our displacement, delta x. When we're pushing it along. And the work that you did was the force times the distance. The force, in my example here, is 5 newtons. And the displacement is 2 meters. And so we've got 10 joules. We did 10 joules of work. Now, we were pushing to the right. But the friction, friction always pushes the opposite way. So the force of the friction is negative 5. It was the other way. And so the work the friction did is negative 5 times 10, which is negative 10 joules. So the friction did negative 10 joules of work. And we could say that the friction has sucked up or taken away your work, and it's your work, the energy from your work is lost now. It's lost in the sense that it won't become mechanical energy again. Yeah, it's turned into heat. Okay, now continuing. But now we have a slightly different example. We're going to, instead of having friction, we're going to have a spring. So we're moving. Okay, so here's this book, and it's starting out with some kinetic energy. You see, it's got a velocity. It's moving at 2 meters per second. The book has a mass of 2.5 kilograms. And, okay, so it's kinetic energy is 1/2 mv squared, plugging in numbers, 1/2, 2.5 kilograms for the mass, 2 meters per second. Don't forget to square it. And so now, doing the math, we find out, okay, it's got 5 joules of kinetic energy, or mechanical energy. Okay, so now the book hits the spring and squeezes the spring. So the book's kinetic energy is 0 because the book has stopped. At least for a moment, it's stopped. And the kinetic energy has been absorbed by the spring. And we say that the spring now has 5 joules. And we're using the letter U to stand for potential energy. So the U of the spring, the potential energy of the spring is 5 joules. Yeah. Okay, so this is all what we just explained. Notice that the energy has not been lost. The energy's been transferred into the spring. Now, okay, yeah. So let's focus a little bit on the signs here. The book, as it was squeezing the spring, was pushing to the right, and the displacement was to the right. So they're in the same direction, the displacement and the force. So that was positive work. On the other hand, the spring was pushing to the left, which is opposite of the displacement. So the spring was doing negative work. And so, yeah, you've got that the spring was absorbing energy. So, yeah, whenever you have an increase in potential energy, that potential energy had to come from somewhere. So it was being absorbed from somewhere. Okay, now the book is rebounding from the spring. The spring has pushed the book away. And the book has now a velocity of negative 2 meters per second squared. Its kinetic energy is negative 2 squared, so that's positive. It has a kinetic energy of 5 joules. And the spring now has 0 joules of potential energy. So, okay, This time, the book did negative work, and the spring did positive work. Why? Well, I can give you two sorts of answers here. First of all, the book absorbed energy. So when you're absorbing energy, or when something is absorbing energy, that it's got to be negative work. The other thing, though, is when the book was being pushed by the spring was pushing one way, but by Newton's third law, the book was pushing to the right. Right. So this was the force from the book, but the displacement was to the left. Right. This is the delta x, the displacement, and so since they're in opposite directions, that's another reason why it's negative work. All right. So we're at the end of this section. I need you to read section 8-1 in the book. So they talk about how gravity can absorb energy, can do negative work. Gravity can do positive work. And so it's very important for you to look at these examples and